Hi everyone, this is Saranya. In this video, we'll be talking about counters. Counter is a device which stores the number of times a particular event or process are occurred. They count the specific event happening in the circuit. Counters has been broadly divided into two categories. They are asynchronous counter and synchronous counter. Under synchronous counter, we'll be seeing about ring counter and Johnson counter, which is otherwise called as twisted ring counter. Let's move to ring counter. Ring counter is almost same as the shift register. The only change is that the output of the last flip-flop is connected to the input of the first flip-flop in case of the ring counter, but in case of shift register, it is taken as the output. In ring counter, number of states in ring counter will be equal to the number of flip-flop used. So let's see the block diagram or the circuit diagram. We are designing a 4-bit ring counter. We'll be requiring 4 flip-flops. We are using D flip-flops here. D0, D1, D2, D3 are the inputs. Q0, Q1, Q2 and Q3 are the outputs. Clock pulse will be common for all the D flip-flops. And the input are RST and clock. Clock can be either positive edge or negative edge. The output variables are Q0, Q1, Q2 and Q3 as I said before. And next is a truth table. With the help of this truth table, we'll be seeing the demo of the ring counter. So we'll be requiring 4 D flip-flops and 4 light bulbs to show the output. And this one is a high constant. And we'll be requiring 1 toggle switch and 1 clock pulse, which has been inputs of the AND gate. And we'll just label them. This is C, this is clock, and this is QA, QB, QC, QD. And this output of the AND gate will be connected to the clock pulse of each and every D flip-flops. The clock pulse is common for all the D flip-flops. We'll just be connecting them to all flip-flops, and now we'll just correct them. Now the first D flip-flop is connected to the Q part of the last D flip-flop, and this Q part will be connected to the this light bulb, and every D flip-flop's Q part is connected to the light bulbs. So you can see that in first D flip-flop, Q is connected to the bulb, and there has been connection between two D flip-flops. We can see between the 4 D flip-flops, and this is the push button, and this push button is connected to a NOT gate, and this NOT gate is connected to the preset button of the first D flip-flop, preset button of the second D flip-flop, preset space of the third flip-flop, and the clear space of the last flip-flop. And this high constant is connected at the clear part of the first flip-flop, and clear part of second flip-flop, and clear part of third flip-flop, and preset space of the last flip-flop. We'll be just correcting them. When we give this push button, we can see the values get shifting. We know the ring counter performs like a shift register, so we can see the values get shifting over here. That is, light bulbs bulb glowing is shifting. So this is the working of ring counter. Let's move to the Johnson counter or twisted ring counter. Alternate name of the twisted type counter is switch tail working or Johnson type counter. The complemented output of ending flip-flop is a feedback to the input of the starting flip-flop, where the streams of zeros and ones are flowing in the ring form. The twisted type counter uses two control signals like clock and ori, where the clock is common for all the 4 flip-flops. And this is the circuit diagram or the block diagram, which has 4 stages twisted ring counter, and they use 4 D flip-flops, and Q0, Q1, Q2, Q3 are the outputs, D0, D1, D2, D3 are the inputs, and clock pulses and ori are common for all D flip-flops. And so we can see the ori or RST will be the input, and clock, And if n numbers of the flip-flop are used, then 2n number of stages are required. The output variables are Q0, Q1, Q2, Q3, as I said before. So the truth table is being given here. With the help of the truth table, we can see a demo of a Johnson counter. We'll be requiring 4D flip-flops, and the high constant is connected to the preset stage of every D flip-flops. We'll be connecting to the first flip-flop and the second one. And this is the push button which is connected to the NOT gate, and this NOT gate will be connected to the clear space of every D flip-flop. So it is connected here, and it will be connecting here. We will just arrange them, and we will be requiring AND gates. The input of AND gates are one toggle switch and another clock pulse. We can just see it here. As I said, one clock pulse and one toggle switch, and they are the inputs of the AND gate, and the output of the AND gate will be the clock signal for each and every D flip-flops, and these clock signal will be common for 4 D flip-flops. We will be connecting it to the third flip-flop and to the fourth flip-flop, and we will just arrange them. Now one NOT gate is being taken here, and this D part of the first D flip flop will be connected to the NOT gate, and the NOT gate output will be connected to the last D flip flop's Q part. As I said, it is connected here, and we'll just arrange them. And there is an interconnection between all the D flip flops. Q and D are connected. Q and D are connected here, and here also it's same. And now we'll be requiring light bulbs to show the output. Light bulbs are connected in the queue of each and every D flip-flops. As I said, it is connected here, it is connected here, it is connected here, and here too. And now we will just label them. This is CS and this is clock, this is QA, QB, QC, QD. So when we give this toggle switch, we can see the light bulb start glowing and it shifts a value. We can see the output here for the Johnson counter. So this is the working of Johnson counter. Thank you. Let's see in another video.